Hello, let's look at the second part of this week, and that is looking at something called divergence. All right, so here are a couple of vector fields to look at. In this first vector field, you can see the vectors are all going outward from some place. If I pick a point, my vectors are all diverging from that point. Diverging from the origin. Okay, in this case, so I have positive divergence. In the second vector field, everything's coming in, converging into zero. Here I have negative divergence. On this third one, it's kind of hard to see, but I tried to draw them so that they were like spiraling inward. So if they are spiraling inward, it does have positive divergence at the origin. Okay, but you'd have to really be able to tell. Okay, if these were not spiraling inward, if they were just going around in circles, okay, and not going inward or outward, then this thing would not have any divergence at all. It would be just like weird stuff. Okay, so zero divergence. Okay, also, like if I'm at this point here, instead of being at the origin, I have just as many vectors going in as I have going out. So at this point, I would have zero divergence. So we want to know what is like the net amount going in or out at any single point. That's what the divergence is. Here's the technical definition. When we have three, we're going to be in three variables. So we're going to take a point. We're only looking at divergence at one point at a time. We're going to make a little sphere about it around that point. And V is going to be the volume of the sphere. And then I'm going to take the flux through that sphere divided by the volume. So notice the volume's always positive. So if the flux is going outward, I'll have positive divergence. If the flux is going inward, I will have negative divergence. So this is like the average flux, because I'm taking the flux divided by the volume about the point. That's kind of how you want to think about it. On average, how much is going in or out at that specific point. Okay. Why should we care? This is going to give us another way to calculate our surface integrals. And here it comes. It's called the Divergence Theorem. If you have a solid shape with no holes in it, so you can't have like a Swiss cheese or anything like that. No holes on the inside. It's solid all the way through. S is the surface, and it's nice. It only has a finite number of sharp edges. So it could be a cube, but you couldn't have like a fractal or like a weird coronavirus looking surface on the outside with an infinite number of little sharp points. Okay? And if your vector field is smooth, first derivatives are continuous, and your orientation is outward, then here's another way you can calculate flux through that surface. The flux through the surface is the outside of the shape, is equal to the total, I'm adding up, divergence throughout the entire volume. So you're looking at each individual point, how much is going in, how much is going out on a net. All right, a net in or net out divergence throughout the entire interior of the shape. And that will give you how much is actually escaping through the surface. So think of it like Brownian motion. Some of that stuff will be going in, but you'll have other stuff that goes out to kind of balance it out. And if you look at that throughout the whole guts of the shape, that'll tell you the net what's escaping out of the surface on the outside. Now, you may have some objections to this because, wait, didn't we say that the divergence was the flux? So I'm saying you can take the flux and calculate it as the divergence, but remember the divergence was the integral of the flux. So it seems like it's kind of circular, but it's not. And that's what's coming up in the next slide. There's an easier way to calculate divergence. And now we need to talk about a little bit of operator theory. An operator is a thing that operates. It works on a function somehow. So you've worked on operators. A derivative is an operator. It works on functions to give you another function. The del operator is an empty symbol. It's a vector. Its first component is simply the operator ddx. Its second component is simply the operators ddy. And its third component is simply the operator ddz. And whatever you do to the function, you're going to work with this operator here. Now, the divergence of f. So if f was a vector of 3 components, then the divergence of f is going to be d dx of f1 plus, oh excuse me, it's not a vector, plus d dy of f2 plus d dz of f3. And the way we usually write it is del dotted with f. So I'd take this vector ddx, ddy, ddz, and dot it with my vector f1, f2, f3. And if you think about how the dot product works, you're going to take your first components, there's your ddx of f1. You're going to take your second components, there's your ddy of f2. And you're going to take your ddz of f3, there's your ddz of f3. It's important to note that these are not really multiplied, though. You're applying the operator to the function, which is not the same as multiplying. When you were in beginning algebra and you had f of x equals 3x squared plus 2, and then they asked you for f of 2, you never multiplied the f times the 2. You plugged the 2 in. So we're plugging the f in. Even though we're writing as a dot, it's not multiplying. It's not. We just write it that way as a mnemonic device to help remember how it works. And we use that because div starts with d, dot starts with d, and the way this works looks like a dot product. All right, let's do an example. Let's calculate del dotted with f for this f. So I'm going to take ddx, ddy, ddz. I'm going to dot it with 3x squared y minus 2xz and 4x plus 2y plus 3z. So I'm going to take ddx of the first thing, which is 6xy, ddy of the second thing, which is 0, and ddz of the third thing, which is 3. So the divergence of this function is simply 6xy plus 3. That's all. Notice it's a scalar. The result of a dot product is a scalar. Now here's where we're going to use this. Okay? Remember the divergence theorem. Where'd it go? The surface integral is the same as the triple integral of the divergence of the function. So now let's try this out. Let's find the flux of this function. Our surface is a sphere of radius 6 centered at the origin, so I'm going to work in spherical coordinates. I'm oriented outward. Okay, so it's the surface, the sphere doesn't have any holes in it. It didn't say that it was like a sphere with a hole in it or anything like that. It's just simply a sphere. Okay, our orientation is outward. My vector field is pretty nice. I don't have any weird continuity problems. I don't have any weird derivative problems. And my surface, the surface of the sphere, is nice also. It doesn't have any sharp points or anything like that. So I can use the divergence theorem, but let's do it by hand first because the instructions say do it by hand. Because we're on a sphere, I'm going to change this into spherical coordinates. So my f is now going to become rho sine phi cosine theta. Y is rho sine phi sine theta. And z is rho cosine phi. Those are just my changing to spherical coordinates from before, gosh, a long time ago it feels like now. Since I am on a sphere, I do know that the rho is a constant, so I can change those to 6's. All right, I need my dA, and in spherical coordinates, this is sine phi sine theta, cosine phi cosine theta, cosine phi times my r squared, which is 36, times sine phi d theta, just know it, and then I'm going to put it all together. So I'm going to take the double integral, because we're doing this by hand, so it's on the surface, of my 6 sine phi cosine theta, 6 sine phi sine theta, cosine phi, dotted with sine phi cosine theta, sine phi sine theta, cosine phi, whoops, I need a 6 in front of that, cosine phi, times a 36 sine phi d theta. And when I'm on the entire sphere, my phi starts at 0 and goes down to pi. My theta starts at 0 and goes all the way around to 2 pi. There's my setup. Looks horrible. Let's see what we can do with it. 0 to 2 pi, 0 to pi, 6 sine squared phi cosine squared theta, plus 6 sine squared phi sine squared theta, plus 6 cosine squared phi times 36 sine phi d theta. Let's see. Those I can factor out as sine squared phi and a 6, and that'll leave a cosine squared theta plus sine squared theta. That's a 1. Ooh, nice. Plus 6 cosine squared phi. I see where this is going. 36 sine phi d theta. Oh, and now this is just a 6 sine squared phi plus a 6 cosine squared phi, so I can factor out the 6 and get a 6 times 1. So this is going to turn into the double integral, 0 to pi, 0 to 2 pi. The 6 factors out, times that 36 makes 108, sine phi d theta. I know you know how to handle that, but we're going to work this 2 ways, so let's actually do this. We're down to 108 sine phi d theta. And phi went from 0 to pi, and theta went from 0 to 2 pi. Remember, phi never goes bigger than pi because it starts here and goes down, and as soon as it hits the z-axis, it's done. All right, so let's see, that's a negative cosine phi, so negative 108 cosine phi from 0 to pi, and my d theta, 0 to 2 pi. So let's see, cosine of pi minus cosine of 0, that's going to be a negative 1 minus 1. So this is going to become a positive 216 when I'm done there, d theta from 0 to 2 pi. And so that's going to be 432 pi when I'm done. Not bad. So it wasn't too bad. It looks horrible, but it's not too bad. Could be worse. Could be worse. But we had a lot to do, right? We had to change everything into spherical coordinates. We had to remember that dA, and then we had a whole lot of trig identities to work with, but they weren't bad ones, so not bad at all. All right, let's do this with the divergence theorem. Okay, my surface is a sphere, so that's nice. I don't have any weird discontinuities. I don't have any weird sharp points or anything like that. My orientation is outward. I don't think it says that on there, but let me put it in. Okay. My surface is not bad. It has beautiful, nice derivatives are nice and smooth. Let's see, my shape, the inside of the sphere doesn't have any holes, anything like that, so I can use the divergence theorem. So the first thing I'm going to do is find the divergence of f. So that's going to be del dotted with f, which is d dx, d dy, d dz, dotted with xyz, which is going to be 1 plus 1 plus 1, which is 3. So I'm going to take the triple integral of 3 dv. 3 is a constant, so because that's a constant, I can just multiply it by the volume. Oh, excuse me, that's not right. I take it back. Yes, dv. I take it back. I can just multiply that by the volume of the sphere. Well, the volume of the constant. So answer is 3 times volume of sphere. Oh, that's easy. 3 times 4/3 pi r cubed, and my r was 6, so 3 times 4/3 times 6 cubed, times pi, and let's see, the 3's will cancel, 108 times 4 times pi, 4 times 108 is 432 pi. Bingo. So lots easier to work. Okay, since my divergence was a constant, this was a piece of cake to do. All right, let's do one more example by hand, and one more, and then that same example with the divergence theorem. I won't do this all the way through, but we'll talk about the setup. So I'm going to find the flux of 2x comma 4, 3. My S is a box, oh my gosh, of sides 2 centered at the origin, and I'm oriented outward. By the way, if you're oriented inward, just like when we did Green's theorem, if I'm oriented in the opposite direction, the answer is just the negative of what I would have gotten. So if this had been oriented inward, no big deal. I would have done it just by using whatever theorem and then taken the negative of what I had. But because this is a box, I've got to do all 6 sides separately. Let me draw this thing first. All right, good. It's centered at the origin, sides 2. So the top is at 1, the front is at 1, the back is at -1, that's at 1, and it goes down to -1. Okay, so it goes down like this. This comes here. That goes like that. Looks kind of like that. Okay, that's at a 1, that's at a 1, that's at a 1, that's at a -1. Down there. And it goes back to a -1. And it goes over here to a -1 as well. So it crosses down here. All right. So let's talk about the top. My A is not hard to calculate. I need to take, these are all parallel to parts of the plane, right? So I can just do it the way we did at the very beginning of the last video. So I can take the area of the top, which is going to be 4, times a vector in the direction of orientation, which is upward, which is going to be k. And so for the top, my flux is going to be 2x, 4, 3, dotted with 0, 0, 4, which is 12. Let's do the bottom. My A, the area again is 4, but if I'm oriented outward, I have to multiply by a -k because outward is down in that case. So I'm going to take 2x, 4, 3, dotted with 0, 0, -4. I'm going to get -12. Let's do the front. Now, for the front, my vector is I, because I'm going in the x direction. The area is 4. So I'm going to have 2x, 4, 3, dotted with 4, 0, 0. Oh, that's a variable. Oh, but in the front, my x is a constant. So that'll be a 1. So I'll have 2 times 4 is 8. And etc. I have to do all 6 sides. So it's not bad. It's time consuming. It's kind of a pain in the neck. It's not hard, just long. Let's see if it's any better if I look at the divergence theorem. Okay. My S is a box. Not bad. It's got some edges, but it only has, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sharp edges. That's a finite number of sharp edges, so that's good. Doesn't have a hole on it or any inside of it or anything like that. The surface doesn't have any holes or anything. I'm oriented outward. Okay, my vector field's pretty nice. So yeah, I can use the divergence theorem. So I'm going to take my surface integral of f dotted with dA, and that's going to equal the triple integral over the entire box of the divergence of f dv. The divergence of f is not hard. It's del dot f, which is ddx, ddy, ddz, dotted with 2x, 4, 3, which is 2, plus 0 plus 0, which is 2. So I'm taking the triple integral of a constant, which means so I'm going to take 2 times the volume of the box, which is 2 times, sides are 2 cubed, which is 2, 4, 8, 16. There's my divergence. Cool. Not bad. Okay, and that is all. Oh, same example with the divergence theorem. There we go. oriented outward. Much easier. If we have time in class, we won't do the flux across the cylinder. We'll look at the shooting a basketball. And we'll discuss other projects and timelines for those as well as we go in class. So I'll see you in class this week. Take care. Bye-bye.